Hi ladies and gentlemen, welcome to Chapter 5. Chapter 5 is all about determinants. We're not going to do a whole lot with the material that's in here. A lot of determinant information is more theoretical and less applied, but there is a little bit that you have to be able to understand with respect to the basics. So we'll just spend 2 lessons on Chapter 5 in order for you to be able to understand what information we can get from determinants, as well as how to use them when we solve for eigenvalues. So to start, we're going to look through the chapter introduction here. This is the Chapter 5 introduction, and I just want to make a couple of highlights for you. The first one is this item here, which is the fact that, sure enough, the determinant is an astonishing number, but at the same time, it isn't necessarily very useful for us. One thing that's really important that you understand is we're talking about square matrices. So a determinant is not defined when a matrix is rectangular. So everything that is in Chapter 5 has to do with square matrices. Another really important result he leads off with here, if the determinant is equal to 0, this tells us that the column vectors are dependent and that A is singular. So this is a really important result. Determinant of A equals 0 implies that A is singular. And we'll talk just a little bit more about that when we start into section 5.1. Other than that, we are going to discuss the cofactor formulas and just the idea of what cofactors are. That highlights some of the important content from determinants. And then starting here, even though he doesn't have it listed, this is really section 5.1, the information he's talking about here, and then we will also do section 5.2. We are not going to cover the material in 5.3. This has more to do with geometry and is really not something that we're interested in. If you want to know what this material is, I highly recommend the Grant Sanderson video on determinants. He does a really nice job of explaining this geometric interpretation. So let's continue on to section 5.1. And again, we're going to look at this introductory material and make some notes about what's important for us here. A couple of these things you already probably have seen before. 2 by 2 matrices are easy to calculate the determinant. And this is really just the back and forth that you've probably seen before. We have A, B, C, D. And the only reason I'm highlighting this is because this kind of back and forth idea is inherent in all determinants, even though, quite frankly, it's difficult for us to calculate anything by hand that's over 3 by 3. So in this situation, we take this product, which is A times D, and then we subtract going this way, minus B times C. And this idea of going from top left to bottom right positive and then going backwards from the top right, bottom left negative is all highlighting some of the important mechanics. So the other thing that I want to point out here, again, this is repeated. Singular matrix has a determinant equal to 0. Strang does not expand on this idea, but it's really important, so let's see what this means. If we have a system, AX equals 0, similarly AX equals B, so we have a homogeneous system over here and a non-homogeneous system on the right-hand side, and we know that the determinant of A is equal to 0. So a couple things. First of all, we know we're talking about square coefficient matrices. So in this case, A is n by n. It's a square matrix. What does it mean that A is singular? Well, in the case of the homogeneous problem, it means that the null space of A is not just the 0 vector, that there is at least a dimension 1 vector space for the null space of A. So we know that the dimension of the null space is greater than 0. Okay. Well, what does that tell us about the problem AX equals B? It means there's no unique solution. If A is singular, we do not have a unique solution. So there's no unique solution. And that's because we cannot solve X is equal to A inverse times B, because A inverse does not exist. So then one of the other two alternatives must be true. Either B is in the column space of A, in which case we have an infinite number of solutions, or B is not in the column space of A, and we have no solutions. Those are the possibilities. So Strang does not highlight this connection, but I want to review this because this is a really important piece for systems of linear equations. All of this information, if we know the determinant of A is equal to 0, which tells us that A is singular. Moving on then, we have an important result here, row exchanges, and as it turns out, column exchanges. If we do a row exchange or a column exchange, we are going to basically take the determinant value and multiply by -1. And so the way he says that is it reverses the sign. So if it's positive, it becomes negative. If it's negative, it becomes positive. That's for each row or column swap that we end up doing. Something that's a little bit more difficult for us to grasp is this idea about the fact that the determinant is linear in a adjustment to any row that is inside of the matrix. So this is important enough that I want to make sure that we get a grasp on it. Let's take again, right, anytime we see something new and we don't really understand, start with simple examples that we do understand and expand from there. So let's just take 2A, 2B, and then C and D, and take a look at the determinant where we have multiplied one of the rows by 2. In this case, we're going to have 2 times AD minus 2 times BC. I've just done the determinant of a 2 by 2 matrix. Well, this is equal to 2 times AD minus BC, but that is the determinant of the original matrix without the multiplication by 2 on the row. So we can see what he's talking about with this linear adjustment when we impact a single row. The same thing is true for a single column of the matrix. If we multiply a single row or column by a constant, then we will have multiplied the determinant by that constant. This then leads to the question, what happens if we take the determinant of 2A? So we're going to take a matrix and multiply all the entries times 2. Well, the determinant of 2A, that's going to be equal to the determinant of A, but not times 2 for every row we have. So it's going to be 2 times 2 times 2 for however many rows we have, times the determinant of A. And this, then, because A is n by n, we said A is square, is going to be n. So we're going to have n of these, so it's really 2 to the nth power times the determinant of A. That's our result. So that is, in a nutshell, one of the applications of, it's not the only one, there are other important results associated with this linearity of the determinant with respect to impacting rows, but this is one of the important ones. And then finally what we're going to do is move into this concept of 3 by 3 determinants and kind of the number of terms that are associated with our 3 by 3 determinants. Really more to come on that. We'll talk about that in a little bit. All right, let's continue on then. We have this information which I'm going to leave you to read down to the 3 by 3 determinants conversation. I think he sums it up really well right here. Determinants lead to some beautiful formulas, but they are pretty impractical when it comes to computation. And we want to understand the ideas. We need to understand the ideas because they're relevant for finding eigenvalues. They're also, as you see here, they're relevant for understanding solutions to square systems, systems where the coefficient matrix is square. But with respect to just their inherent purpose, they're not that interesting. Let's take a look at the 3x3 determinants and the example. Again, he makes a very insightful comment right here. 2x2 matrices are easy, 4x4 or larger matrices are generally hard. We're not going to do those by hand. So what lives in the middle are the 3x3s. There's a lot of insight to be gained by understanding how the 3x3 determinants work, and we'll do a little bit with that, and let's proceed right now. So we're going to leave you to read this material here so that you get some idea about the determinants and the whole concept of the row swaps. And he continues the conversation through a generic matrix. So let me put this at the top of the page here. And what we want to do is copy down this generic matrix that he has. It's a little bit awkward actually. Let me write it down. So here's the matrix that he references throughout section 5.1. And I just want to write this down so that you're familiar when he's referencing these different combinations of products. But what he demonstrates over here is what I like to call the pitchfork method. Many of you may have seen this before. This comes up regularly in physics class, for example, or Calc 3. And this is nothing more than the expansion of the idea we talked about. We have the positive products coming in the top left to bottom right, and then the negative products from the top right to the bottom left in this manner. And we end up with these 6 terms, and this is what he's talking about with respect to the number of terms. It's n factorial. So if we have a 4x4 determinant, we have 24 terms, each of them with 4 values in the product. And that's where it becomes very difficult for us to be able to do any computation. So he works through the 1x1 and the 2x2 and the 3x3 examples here. Make sure that you understand those. And he makes a really important point right here. Right? Each one of the terms involves one number from every row and every column. This is a hallmark of determinants. This is an important piece of the understanding. Every one of these products takes a number from a row and column that are all separate from one another. So from each row and column we get one number only. And that we'll see in a moment when we look at the 4x4 example. He says a little bit more, read through here about the 3x3 and the 4x4 examples, but what we want to look at is this, and I want to break this down for you so that you understand what it is that he's talking about. Okay, he says, now we move to the 4x4, which we know has 24 terms. Here's a key simplification, and it will teach us a lot. 4x4 determinants come from 2 3x3 determinants. Well, for his specific example, that's true. Let me explain what he's saying here. So it turns out that this 2 is actually this 2 here. And when that 2 is in the first row, first column, so when we eliminate the first row and first column, the column and row that contain the 2, we're left with a 3x3 matrix. And that 3x3 matrix is down here, and that's the matrix that he's finding the determinant of. Then he goes to the next term in the row, and I'll use orange for this. He goes to this term. That's the -1 we have right here. And the matrix that's left over, once we pull off the first column and, the first row and the second column, we're left with this matrix. And Strang can avoid putting in the zeros. You cannot. If you're going to write down these matrices, you need to include the zeros. So the matrix that's left over is the -1, 0, 0 here, and then these 2 abbreviated columns over here. The -1, 2, -1, and the 0, -1, 2. This is called cofactor expansion. And we're going to talk more about that in just a moment. This is a means of calculating determinants. And really the cofactor expansion is an important way for us to understand, and we're going to spend some time talking about it. We can do this by expanding and calculating cofactors, which we haven't defined quite yet, but we will in just a minute, along any row or any column. And I'm going to work a specific example for you. So I think that Strang's discussion down here is adequate, but I think it leaves us a little bit wanting to understand. So read through this, but what I'm going to do is I'm going to give you a specific example about cofactor expansion. And we talk about cofactors, and he gives us the formula down here for the determinant. All he's done is taken the 6 terms that he showed us earlier and rearranged them. Remember that generic matrix, the ABC and the PQRXYZ, he's using the same variables or letters, if you will, here. And we'll get to the cofactor definition in a minute. What I want to do is just show you an example because I think it will help to make this clear. Let me write down the matrix we're going to work with. All right. What we have here is a matrix where we immediately know what the determinant's equal to. In this case, the determinant is equal to 0 because the columns in this matrix are linearly dependent. That's not what we want. We want to actually do a demonstration, so I'm going to change the 9 to a 7. And then what I'm going to do is, and there's a demonstration in the text, he walks through an example, I want to do another one. And I'm going to do cofactor expansion, except I'm going to do it along the 3rd column. So his example in the text is along a 1st row, which is fine. I just want to show you something different. So the way cofactor expansion works is we start, and it doesn't matter which column or row we use, the idea is exactly the same. We're going to start with a value. In this case, we're going to start with with 3. So we're going to take the value of 3, and then we're going to multiply it times the determinant of the matrix that's left when we remove the row and column that contains the 3. So we have the 1st row and 3rd column, and what we have left is determinant of the matrix 4, 5, 7, 8. Just so you know, these single lines are often used to designate determinant instead of using the word DET. It can be a little bit confusing because it looks almost like a matrix, but it's not. They're just straight lines like absolute value. They don't have the little ticks on the top and the bottom of the brackets. Then what we do is we just move down and go through all of the elements that are in the particular row. So let me change colors. I'll change to orange. The next one that we're going to do is the 6. And so we're going to have 6. It turns out that we need a negative, and I'll explain where the negative comes from in a little bit. We have negative 6 times the determinant of what's left after we cross this out. And we can see what's left is the 1, 2 and the 7, 8. That's the part that's remaining. And then finally, and let me do it in blue, we're going to have a 7. So we have a plus 7 times the determinant of what's left once we remove that row and column, which is just this part right here, the determinant of 1, 2, 4, 5. So this is an easy way for us to be able to take any size matrix and break it down, because if we didn't know how to do the determinant of this matrix here, we could just do cofactor expansion again along one of the columns or one of the rows. So I'm going to pause and write out all of the arithmetic here. All right, so this is the arithmetic associated with the determinants of the 2 by 2 matrices being multiplied times each of the values that are in that position. And the only thing we have left to discuss is the negative. So the negative really comes from the idea of row swaps that will give us the matrix that we want. So if we think about this, and this is not generally the way it's explained, but I'll tell you the standard definition down here when we get to it. But if you think about the 6, how many row swaps and column swaps would be required for me to move the 6 up to the position of the 1 here? Well, I can't just swap the first and third columns because that's not going to end up with the same matrix. I have to do this piece by piece. So it's going to take one row swap to put it in the middle, and then, one column swap to put it in the middle, another column swap to put it over in the first column, and then one row swap to put it on the top. So that's 3. So I would need column swap, row swap to put it in the 1, 1 position. That's 3 swaps, and we know each swap gets us a multiplication by -1. So -1 times -1 times -1 is -1, and that's why we have a negative here. Similarly, for the 7, I'd have to do 2 column swaps, swap, swap, and then 2 row swaps, swap, swap, and that would be 4. And of course, -1 to the 4th power is positive, and that's why this gets a plus. So there's an easier way to think about it, but that's what's really going on kind of behind the scenes. So once you do the arithmetic here, we come up with a determinant of 6. If you had done the pitchfork method, you would of course come up with the 6 anyway. So read through this conversation about the cofactors. That's important. And now let's just talk about what the cofactors actually are. And you'll see that we just finished calculating some of them. So for the ij cofactor, and the way we designate that is with the C sub ij. So that particular cofactor is created by removing the jth column and the ith row, just as we demonstrated, and then taking the determinant of what's left. So we're going to remove the row I and column j from the matrix, and then this cofactor is equal to, we'll get to this in a minute, times the determinant of the remaining matrix after we remove that row and column. This -1 to the I plus j is accounting for the row swaps that we talked about that makes it negative or positive. So again, coming back up here, this is in row 2, column 3. So row 2, column 3, we add those together, we get 5, and 1 to the 5th power is -1. That's why it's a negative. Whereas the 3 is in row 1, column 3, and that gives us 4. So we have row 1, column 3, totals 4, 1 to the 4th is +1. That's all this information here is. And so that's how we calculate a cofactor. Let me just be clear with the example that we did. So the cofactors, this, okay, that is equal to the cofactor at 1, 3. Okay. Sorry, I misspoke. This is a very common mistake. Don't make the mistake I just made. The cofactor is this thing right here. It's the determinant once I've removed those values, and then it's multiplied by a positive. So this, along with the negative sign, is the cofactor at 2, 3. What's important to understand is the piece that's not included. The piece that's not included are the numbers out in front. Those are not part of the cofactors. The positive or negative sign is, but not the values from the matrix. So the things that are not part of the cofactors are the actual values that are in the matrix along the column or the row where we did the expansion. That's not part of the cofactor. And so then the result is the cofactor formula for finding a determinant, at least along a row in this particular case, is the determinant of the matrix is equal to the value times its associated cofactor. So when we did our expansion here, the value 3 is multiplied times the cofactor of what's left once we remove that first row and third column. And then we just walk our way along a row, just like I showed you in the example, or down a column. It'll work either way. And understanding this formula and understanding how you can use it compounded is something that we want to make sure that we understand. So beyond that, Strang gives us and starts talking about, well, we could build a matrix, which he calls the matrix C, which is equal to, for example, C11, C12, C13, etc., C31, C32, C33. We could build a matrix filled with the cofactor values. Cofactors are numbers. It's a determinant times a positive or a negative. So we could fill a matrix with these things. It would be a tremendous amount of effort computationally to go in and do that, which is why we don't do it. But the idea is there, and we're going to just brush on this idea. We're not really doing anything with it. I will tell you, you can generate a formula for the inverse of a matrix by taking the transpose of this. So the inverse of a matrix is equal to the transpose of the matrix that's defined up here, divided by the determinant. This is one of these clever formulas that contains the determinant. It's not functional, and we're not going to spend much time on it. So you can take a look through this information, but I wouldn't spend any time on it if I were you. Instead, what you want to do is you want to look at this example that he talks about, where he's talking about using the cofactors and doing the cofactor expansion. And he shows us how to come up with the determinant that he found earlier. So you definitely want to take a look through that. Don't worry about the adjugate matrix, right? This matrix which is filled with the values of the cofactors. That's not really what we're covering. One last item that's very important, which is the cofactor formula, which is the formula for finding a determinant, is most useful when we have a matrix filled with zeros. Let me give you another example. All right, so what we're doing here is an example of a determinant for this particular matrix. Well, if we're clever, we can actually make a really good decision here. What we want to do is we want to expand this matrix along the second row because it's full of zeros. It's 0 multiplied by some determinant, in this case negative 2089, although I don't really care because that's going to be equal to 0, and it's actually a negative 0. And then it's plus 0 times another determinant that I don't care about, 7009, because 0 times that determinant is just 0. And then finally, I have a negative 1. So I'm going to expand right here, and I'm not going to use that row or that column. So I have negative 1 times 7, negative 208, this determinant. Well, that's easy enough. That's equal to negative 56. And that's all it takes to find the determinant. The determinant of that matrix is negative 56. So the cofactor formula, the idea of expanding along one of the rows or one of the columns, is not only theoretically useful, but when we have what we call sparse matrices, matrices that have a lot of zeros in them, it's actually a computationally effective way for us to be able to do this, because we can quickly find determinants without having to go through the procedure that we'll talk about in the next section. So that's it for the content for today. All we have left are the questions. Let me throw these up. These are the participation questions. So for lesson 20, what we're going to do is just consider this and just some practice with cofactors. So what you're going to do is you're going to list cofactors found by expanding along this second column here. Okay. And then you're going to do a little bit more, which includes a row swap in order to find the determinant of B based upon the determinant of A. And then finally, you're going to do some 2x2 matrices just to practice very quickly. Make sure you've got it down, right? This product minus this product. And then also look at when you multiply these matrices together, what do we end up with for determinants? Because this is one of the most important results that we're going to have from chapter 5. That's it. Thanks.